Next presentation is a new design of multifocal plane microscopy.
Hello, thanks for coming. I'm Dong-Young, this is Dave. Today I'm really excited to present our project titled A New Design of Multifocal Plane Microscopy. We are working with the World of Lab in UT Southwestern, and we construct a new microscopy setup. The multifocal plane microscopy is one of the, we put it on, one of the novel fluorescence microscopy technique that can imaging the multifocal plane at a time simultaneously, so that the life-cell imaging in 3D can be done with these techniques. The panorama image on there, that would be using kind of garage, but we put a nice, beautiful mindset on there with the position station and the self-reproduction station. The picture on the right bottom side here, this shows the top and the front view of the mount setup. And this setup has 4 cameras, which means 4 different focal planes can be imaged at a time. And we installed the piezo, lasers, and shutters, and the object warmer. And all these electrical devices controlled by a software we developed. We call it C, and this with the NI CDI. So using this setup, we do some biology experiments. And one of the experiments in the top on the side, that image is the HMAX sample. And the 3D image is reconstructed from the mount image on the side. Okay, this was our initial plan for the senior design, but we do one more step. That is the super resolution. The classical microscopy, the resolution limit of the classical microscopy is about 200 nanometer in XY and the 500 nanometer in Z. But using the super resolution microscopy technique by Palmer Stone, we can enhance it like 20 nanometer or less. So we do the super resolution microscopy, and we also develop some software that analyze the super resolution images. And that is the final reconstruction image of the super resolution microscopy. This is the image of the BP474 breast cancer cell, and the classical microscopy image, you can't see anything, it's just hazy. But in super resolution microscopy, you can see some punctuated structure, which is perceptive and transparent. And the next is using these 2 technologies, the MOM and the super resolution, it might be possible to do the imaging the 3D live cell in super resolution. And I believe that might be a kind of revolution in the microscopy imaging field. Thank you for listening, and thanks to Drs. Ober, Boris, and Ram, Chow, Anthony, and the PhD students, the Anish, Ramraj, David, and Jeff. Any questions?
How much of what you're showing there in terms of the physical layout in that little picture at the bottom do you guys implement yourselves?
Okay. This is the scientific machines, and there's a 4 scientific camera, which is very expensive. And we also put the piezo, which is control the 10 nanometer system. And also there's a lot of equipment including microscopy, so it's really expensive. And this is supported from the World of Lab in Southwestern, and one of the we do one of the projects they have. Yeah.
So you actually did the assembly?
Yeah.
Okay.
This was actually, yeah, we did the
assembly, and you wrote the software?
Yes, right.
And the software is running on that station?
Yeah,
left on the screen?
It is. Unfortunately, there's no space for the software, but we have a nice GUI.
And the images that you're showing us, they come from your software?
It is, yes.
And there's just 2 of you guys?
Yes. And yeah, right. Yeah, honestly, I don't really a lot.
So honestly, from my personal standpoint where I'm sitting, having just watched a parade of projects that failed to achieve anything with a team of 6 people in 2 semesters, the 2 of you guys have done a phenomenal job. Absolutely phenomenal job.
Yeah.
I hope you get jobs out of it. It really is.
Yeah, even we did the biology experiment as well, so yeah, I learned a lot from this project.
I think you should be very proud of it.
Yeah. Thank you so much.
A 20 nanometer device is very valuable.
It is. Yeah, that's why I'm saying the super resolution, and that is by the mathematically estimated points. Yes. So we use kind of a maximum the neighborhood algorithm things, and we the kind of fitting of the point spread function, which is one of the function of the light described in mathematics. And using that mathematical technology, we made a reconstruct an image. Yes.
And the process is optical?
Yes, optical and mathematically processed.
And then looking at the image with a camera?
That is, maybe I want to explain about the super resolution imaging itself, because the way of imaging the super resolution is a little bit the kind of takes of time, which means you can't, if let's say there's 2 points, you can't distinguish these 2 points. But let's say if you turn off one of this, and if you can see one on there, and you can estimate the points, which is like 10 nanometer or less, and then you can turn off this, and you can turn on the next one, and you estimate this, and then you can see that there is 2 points rather than 1 point. So this is the basic diagram of super resolution, and we make something kind of chemicals, we put the chemicals up in the fluorescence and then make this kind of image. Yeah, it's a little bit tricky.
So I will point out, most of your design teams you've seen, it's always been usually 3 to 6 students. Here there was only 2, but we allowed this one because they were engaged with other researchers from UC Southwestern as part of the process. They weren't not supposed to do any of the work. They were supposed to communicate and engage on a regular basis.
Yeah,
Who's the sponsor?
The Dr. Over.
Brandon Over, he's a faculty member in our department.
Okay.
Any other questions?